All right, today we're going under the hood of a truly massive digital system, one that literally holds the legal futures of millions of people in its code. This is the blueprint for a federal immigration system, and it is an absolute masterclass in high-stakes engineering.
So this is the big question, right? This isn't just some tech challenge about storing data. We're talking about a monumental task with huge national security implications and, of course, a profound impact on individual human lives. The stakes just don't get any higher.
You know, any great piece of engineering really starts with one simple question. Who is this for? Before we can get into the databases and the security protocols, we have to understand the actual people who will be depending on this digital front door. And this system has to work for a huge range of users. On one end of the spectrum, you've got the public, the applicants and their lawyers, who just need a simple, clear way to submit their information. But on the other end, you have USCIS officers making life-altering decisions, and even external agencies like the FBI and DHS, who need secure, reliable access. Building one system for all these different needs, that's the core challenge right there.
Okay, so you don't build a digital fortress of this magnitude on a whim. You start with a detailed, really exacting blueprint. And in software engineering, that blueprint is a set of requirements that spells out not just what the system needs to do, but how well it needs to do it, especially under pressure.
And this slide shows a really crucial distinction. Over on the left, you see the functional requirements. That's the what it does part, like letting you upload a document. Pretty straightforward. But on the right, you have the non-functional requirements. This is the how well it does it part. And this is where things get really intense. We're talking extreme reliability, massive scalability, and just absolute airtight security.
And when we say extreme reliability, we really mean it. The target is this number, 99.99% availability. They call it 4 nines. So what does that actually mean in the real world? It means the entire system can only be down for a grand total of about 52 minutes for the entire year. That is an incredibly high bar for any system to clear.
So, with those requirements burned into our minds, let's follow a single application on its journey. Think of it like it's passing through a series of secure checkpoints inside this digital fortress, and we can see how all the pieces work together in this carefully choreographed dance. This flowchart gives us the play-by-play. It all kicks off with a secure login. Then, once the user submits their forms and pays the fee, which, by the way, is handled by a completely separate and secure treasury service, the system just springs into action. Look right here. This is the cool part. Background checks are automatically kicked off with other agencies. A unique case ID gets generated, and only then does the application finally land in front of a human review officer. Every single one of these steps is tracked and secured.
So what's the engine making this whole journey possible? It's an architecture style called microservices. The best way to think about it is instead of building one giant monolithic program, the system is broken up into a bunch of smaller independent services. It's like our fortress having separate specialized buildings. One building handles payments, another one stores documents, a different one sends out notifications. The beauty of this is, if one building has an issue, it doesn't bring the entire fortress crashing down.
Now let's get to what is arguably the most critical piece of this entire puzzle. We're talking about millions of files with some of the most sensitive personal details you can imagine. Security here isn't just some feature you tack on at the end. It is the absolute foundation of the entire system.
And the whole guiding principle is something called zero trust. You see, the old model was like a castle with a big wall and a moat. Once you got inside, you could pretty much roam around freely. Zero trust completely flips that. It assumes no one is trusted by default. Even after you're past the main gate, your ID is getting rechecked at every single door you try to open for every single action you try to take.
And zero trust is just the philosophy. The data itself is locked away in a vault with multiple layers. It's protected by military-grade encryption, both when it's just sitting on a server and when it's flying across the internet. The public website is completely separated from the internal systems officers use. And everything that happens, every click, is basically carved into stone in these unchangeable logs, all while being watched over by a 24/7 security team.
Let's face it, the world is unpredictable. A policy can change in an instant, a global crisis can pop up, and this system has to be able to handle these massive, sudden surges in applications without even breaking a sweat. It has to be built for any storm.
And these storms are very, very real. As you can see from this chart, a single policy announcement can cause traffic to just spike overnight. The system can't wait for a human to run and add more servers. It has to be smart enough to scale itself up automatically and instantly to meet whatever demand comes its way.
But what about a real disaster? I mean like a whole data center getting knocked offline. Well, the recovery plan is nothing short of incredible. Think about it like this. The first number, the RPO, sets the goal for data loss at no more than 5 minutes worth of information. The second number, the RTO, is the target for getting the entire system back up and running from a backup location in under 30 minutes. That's just wild.
So all of these design choices, from the way it's built to how it recovers from a disaster, are about way more than just the here and now. This blueprint is also a foundation for the future, and every single choice represents a really carefully balanced trade-off.
This slide is so important because it shows that every choice is a trade-off. For example, look at the database. They use a more traditional relational database. Why? Because for legal records, you need absolute, total certainty that the data is consistent and accurate. Other, newer databases might be a bit more flexible, but they just can't offer that same ironclad guarantee. It's a trade-off. You sacrifice a little flexibility for untouchable integrity.
And this is where that solid foundation really starts to pay off. It's built to support the next wave of tech. We're talking about AI that could help officers spot subtle fraud patterns a human might otherwise miss, or software that can automatically read and pull key information from thousands of documents. This frees up officers to focus on the really complex cases. This is how you start to actually tackle backlogs and make the whole system smarter.
And that really leaves us with a final, and honestly, a crucial question. Building a system this powerful and this efficient is an incredible feat of engineering, no doubt. But as this technology keeps evolving and getting smarter, the challenge starts to shift. How do we make sure that the systems making decisions about people's lives are not only secure and fast, but are also fundamentally fair, transparent, and humane? That right there is the next frontier.